All right, let's get into the drop jump and ultimately integrating the grand reaction force curve from a drop jump. So I'll take a couple videos to do this. So I've got a box here and I've got my force platform embedded in the ground right here. And I've got my person who's going to start standing on the box. It's a funny person. They're going to step off the box. And then that's supposed to be a leg. Now it's nothing. Okay. Okay, we'll go creative here. So we're going to step off the box, land on the force platform. Get low, and then ultimately jump off into the air again. Okay. So stepping off the box, landing, and there's even a moment right here where they're landing on the force platform at a low position, jump off, and then up into the air again. That's jumping high. Okay. Yeah, that's not bad. T1, T2, T3, T4, T5. That's the task. That's the drop jump. And then they land again, maybe somewhere over here. I've got one force platform, and I can only, when I record this force platform data, I'm only going to be recording the time, or excuse me, I'm only going to be recording whenever this person is in contact with the force platform. I still said that wrong. Let me draw it, and I'll try to draw it in line with that. This is, let's stay with FZ as vertical. Time on this axis. So let's say I start data collection, time 0. I say go, all right? They're standing on the box. What's my force platform going to read? 0. Why 0? Well, 0 because the person's not contacting the force platform. Are there forces acting on this person? Yes. Gravity, kinetic analysis, gravity pulling down on the center mass, and this box is pushing up on the person. I'm not recording that force. Okay, I'm not recording that force. So I really can't figure out my kinematics because F equals ma, the forces acting on the person include this force that I have no idea how much it is. I know gravity, that's just the weight of the person, but I don't know what this is. So as long as that foot is in contact with the box, I can't figure out ma at all. I can't figure out acceleration at all, okay? I can only start doing something with understanding kinematics when I know all the forces acting on the person. And that's the moment they touch this force platform. And then once they're off into the air again, whoops, force equals ma. That's supposed to be an equal sign. All right. Now here I know it's a projectile and there's only gravity acting on the person. But once the person lands again, once they land again, okay, now I've got them contacting this area over here, which is not a force platform. And so now, once again, I have a force acting on the person from here, plus gravity. If I add up the forces acting on the object, I'll get a mass times acceleration, but I'm not measuring this. I'm only measuring from one force platform. So this makes drop jump really sort of a bit of a challenge to do some analyses with. Now, one thing I could do is have the person jump up in the air and land back on the force platform, and then I would get this contact again. Or I could use two force platforms. We have two in the lab, and I could take off one and land on the other. But if this is not an instrumented area of the ground, I'm not able to do my kinematic analysis from my kinetic analysis because I won't know all the forces acting on the person. This force right here will be unknown, and acceleration would be unknown. I have two unknowns. You can't solve an equation when you have two unknowns. Here, I know all the forces acting on the person. I've got gravity and I've got the ground reaction force. I'm measuring the ground reaction force. I know what gravity is. That's the person's weight. I know the person's mass. I have one unknown, acceleration. I can solve for that acceleration. All right, so back to the force tracing for the ground reaction force. It'll look something, it'd probably get a spike, something like this, and then off into the air again, okay? Off into the air. And this will continue to measure zero, and this would be zero as far as, I want to go to the left, even though there's another force acting on the person back here, but I'm not measuring that force. I don't have any instruments on this box. So my force platform reads zero because the person's not in contact with the force platform. I know that seems obvious, but this is a critical part to doing kinetic analyses and using the force platform. In order to do a kinetic analysis to yield kinematic data, I need to have my movement occur such that I'm measuring all forces acting on the person, or I know forces acting on the person, in this case, gravity. Once that person's foot is off this force platform, even partially, my data are bad. Because once that person's pushing on a part of the floor that is not instrumented, I'm not measuring that force anymore. I'm still measuring something if the foot is partially on the force platform, but I'm not measuring the full ground reaction force. So this is where we need to be really careful when we're collecting data to make sure the person, when they are doing a task like a drop jump or running or walking or even a counter movement jump, that they are on the force platform fully in order that we're measuring that force. And then we can put all the forces that we know or have measured into this equation. All right, so this would be my typical force tracing. Maybe it gets a little more complicated depending on my instructions to the subject, but I'll probably get an impact peak and something else going on here. So now I want to analyze these data. What I have to do is, and I'll do this in another video, is I have to identify a criteria for ground contact and a force criteria for takeoff. And a typical criteria is a force threshold of 20 newtons. I'll exaggerate here, okay? This dotted line representing 20 newtons, 20. That's a very typical force value to use. Sometimes we may go as high as 50 newtons, all right? It all depends on how much noise we're actually measuring in our force platform. So why not go down to 1 Newton? Well, we don't go to 1 Newton because our force platform has easily in the Kistler system, and when you record on Bioware, you easily have plus or minus 5 Newton noise in that force platform signal. So I can't go to a force threshold of less than 5 Newtons, or really state I don't like to be anywhere near 5 Newtons, because every now and then you might get a weird spike, and then you're triggering your algorithm to extract data from that point. So why not go to 10 Newtons? Well, you could. 10 Newtons is still sort of close, and 10 Newtons is not a lot of force either. So 20 Newtons is pretty well an accepted force threshold for contact. Now that might change if I'm doing, kids or people who really don't weigh a lot, because that 20 Newton well, divided by 4.4 and you get pounds. So you get a sense for what that what that value is. All right, but when I'm extracting the data, I'm going to look for the first force over 20 newtons. Now I drew my line here, but first force greater than 20 newtons. Okay, that would indicate, I'll draw it thicker so I can be lazy. That will indicate contact. Then on the takeoff end, I look for the first force below 20 newtons. Okay, so right here. Now, really what I do in my code is I look for a continuous amount of forces below 20 newtons. So every now and then you might get some funny tracings, like the data may say 50 newtons, then it may say 32 newtons, and then maybe it goes to 15 newtons, but because there's plus or minus 5 newtons worth of noise, it may actually go back up to something like 22 newtons. That's 7 newtons, but that's okay. And then maybe it goes down to 16 newtons, then 15 newtons, and so forth. What my code I typically do is I look for that continuous data set that's below 20 newtons. And that one may just be an erroneous signal, and we have to deal with that later on. And that just sort of helps making sure that we're getting the point where the person is leaving the force platform. And same thing over here. I look for continuous forces greater than 20 Newton. And then I go back and I take that first continuous force that's greater than 20 Newtons. Okay, so then I extract these data for analysis. And I don't care anything about these data, and I don't care anything about these data over here. I just get rid of them. And I only pull out the data set that I'm going to use for analyzing the drop jump. In my MATLAB code, I may put this in its own file at that point. I always keep my raw files, so I don't overwrite my raw files, and I'll create new output files consisting of just the extracted data, because maybe later on I want to read those extracted data in, and I don't want to have to deal with finding that contact or takeoff again. Okay, so we're going to pull those data out for analysis. Now we want to integrate this drop jump. And what I've talked about in other videos is the trick with integrating is to know your initial velocity. Now, when we do a counter movement jump, where the person's starting from a standing position, then their initial velocity is 0. But in the drop jump, the initial velocity at contact is not 0. Okay, they're moving downwards at this moment in time. Therefore, the initial velocity is some negative value. It's something less than 0, negative indicating downward movement. And then over here, obviously, velocity is going to be going upwards. All right. So what we need to do is figure out some velocity when we're integrating. We need to know one velocity. And what we'll typically do in a drop jump is we'll figure out that initial velocity based upon the height of the box that they're stepping off of. Now, that's limited, that there is some confounding factors with estimating contact based upon this height, and I'll go through it in a second. And this is where your instructions to the subject become really important. And we need to tell the subject not to jump upwards off the box, not to drag their foot off the box, but to step off as cleanly as possible so that they're leaving the box at the height of the box. And then they're going to fall that distance, that displacement, and then hit the ground. Is it always going to be that amount? No, it's not. But that's partly why we do repeated trials. Or we take a condition, we may do 5 trials or 10 trials or whatever it is. And that way we can sort of capture a range of error and average that error out over all the trials. All right, so we want to get initial height from this box. So what do? We pull out our standard equations for constant acceleration. And we're going to drop an object from this height. I'll just draw it like that. Okay. So this is some height. It's a projectile. Okay. What are our equations of constant acceleration? Well, we have SF equals 1/2 AT squared plus VIT plus SI. That's one of the equations. In this case, we're dealing with projectile, so acceleration is negative 9.8 meters per second squared, the acceleration due to the force of gravity. All right, so what do I have here? I've got height. That's all I know right now. I don't know anything else, because remember, I don't have any indication from my data set. This is all I have. I have no indication as to when the person stepped off the box. No indication. I don't know if it was here. I don't know if it was over here. I have no indication of when the person stepped off the box. So I do not have any time. I have A, that's known. Initial velocity, I don't know that either. I do know SI and I know SF. So this would be, and I always use S, I don't know why. SI and SF, I know those two positions. So I know that, I know that, I don't know that, I don't know that, I don't know that, I know that. I have two unknowns, initial velocity and time. That's the wrong equation. All right, so now let's move on to another equation of constant acceleration. You should just know these. This, by the way, is just a second order polynomial. And you know the shape of a projectile when in air is a parabola. Right? That's a second order polynomial. 1/2 AT squared plus VIT plus SI, second order polynomial. So our other equation of constant acceleration is VF squared equals VI squared plus 2A delta S. Okay, so now let's look at this equation. I know delta S, because that's what this is. I should have done it that way. So that's known. I know A, that's negative 9.8 meters per second squared. And I've got these two velocity values. This VF is going to be the velocity final. This VI is going to be stepping off the box. And we need to give appropriate instructions so that person's initial velocity when they leave that box is 0. Okay? And this is why you do need to have people practice, and you got to give them good instructions so that they're just stepping cleanly off that box. Therefore, we know that. And I'm left with one unknown. So now I just rearrange the equation. VF equals, that's a 0, the square root of 2A delta S. And if you've done any reading in jumping, you'll recognize this equation. 2 times the acceleration due to the force of gravity times the displacement final position minus initial position. And notice you can still use negative 9.8 meters per second squared here, because 2A SF minus SI, as long as your reference frame is up as positive, SF is 0, SI is some number, maybe 0.5 meters. 0 minus 0.5, that's a negative number. That's a negative. That product will be positive. Multiply by 2, take the square root, and I solved for VF. That VF is the velocity at landing. And that's the velocity that we're going to start our integration of the ground reaction force to yield acceleration, and integrating the acceleration profile to yield velocity. Okay, I'm going to end this video there, and I'm going to pick up on doing the acceleration to velocity, I'll do force to acceleration to velocity and to position on another video. Okay, thanks.